Hello, this is the next video from the series on the bracket-proof notation. And in this video, we are going to look at some examples of how to set up basic types of statements one needs for various mathematical statements as basic ingredients. How to set them up by combining the building blocks for setting up mathematical statements that we discussed in the previous video. So let's start with the following example. Suppose I want to say, and this is something that happens very often in mathematics, that you want to say that you've got an object that has a certain property, but there is only one such object. So we usually say there exists unique x such that something something. And so now the question is how to write this out using the logical symbols that we've introduced in the previous video. So these are the basic logical symbols that can be used to set up any kind of mathematical statement. So let me write down here what we want to express mathematically. So let's say we have some statement alpha that deals with an object x. So alpha says something about x. Alpha could be saying x is bright, if x is a color, or it could be saying x plus 1 equals 5, if x is a number. Anything at all. Doesn't matter what alpha is. Whatever we're going to discuss now will apply to a general alpha. And so what we want to say in mathematical symbols is that there exists unique x such that alpha x is true. So we want to say there is only one x. So first of all, there exists an x, and secondly, there is only one such. And now this thing I just said now, the breaking up of this exists unique into two parts, that exists and there's only one, is going to be useful actually, because that's how it will be set up also with the logical symbols. So we have a logical symbol for there exists. It's this one. And if I say just this, then all I'm saying is that such x exists. It doesn't say, this thing doesn't say that it's unique. Unique means that there is only one such. So it means that there cannot be another object having the same property. Well, I could literally say that in symbols, right? I said there cannot be another object having the same property, so I could say, okay, it's not true that there exists something else, something that's different from this one that we know exists, right? So it's not true that there exists something else that's different from x. And at the same time, alpha x is true. And then I could maybe combine these two with a conjunction, because I want both of these things to be true. There is one problem though in what we see here now. And the problem is that when we introduce a variable under a quantifier like the x here, this x has a meaning only in the scope where the quantifier applies. And in this case, the scope is given just by the alpha x. So there is invisible brackets here. You know, sometimes we drop brackets in mathematics because it's obvious what their placement should be, and then we drop them. And so there is this invisible bracket here that should be there, but we dropped them because it was not necessary to to use them. But then if we place brackets like that, then it really becomes a problem because of what I said before, because now this x only exists here. So the x only has a meaning between these pair of brackets. And so I cannot refer to x here anymore. If I want to refer to that x here as well, then I need to extend the scope of this existential quantifier. It shouldn't end here. So then it means that the bracket should be placed not the way we did, but rather it should be placed here. So the closing bracket for that matches with this one. Now if I place the bracket there, then there is no problem anymore. We're now saying that there exists an x for which alpha x is true, and at the same time, you see we've got the and symbol here, at the same time, it's not true that there also exists a y different from x and having the same property, except I made a little mistake here, right? This shouldn't be x, this should be y. Right here, we should have y here, not x. We want to say that there exists a y that's different from x, but still the same property alpha holds for that y. Okay, so that expresses that there is a unique x. So in mathematics, when we say something is unique, that this is what we mean. We mean that it exists, and we mean also not only that it exists, that an object x exists for which alpha x is true, but also that nothing else can make alpha x true apart from that single one. So there is only one such x for which alpha x is true. There is another way to write out the same thing, that exists unique x such that alpha x is true. We can also write it out in a different way, where we do actually entirely separate the two parts. We're going to now separate this into the part that says there exists at least one x, there is at least one x such that alpha x is true, and the part that says there is at most one such x. There is at most one x such that alpha x is true. Now, the left-hand side part will be expressed in the same way as we did the left-hand side there. So there exists x such that alpha x. And we will treat this as one separate statement, and we will take its conjunction with another one that will say that there is at most one such x. Now, how do we say that there is at most one? Well, what does it mean for there to be at most one? We have to ask that question to ourselves. What does it mean for there to be at most one? Can we explain that in more basic terms? So if you think about it for a little bit, you might want to pause the video here and think about it on your own. If you think about it a little bit, you will start thinking of because remember, I mean, we can only quantify in two different ways. We can quantify to say something, that there is at least one thing, and we can also quantify to say something should be true for all, right? And the existential quantifier doesn't seem to be applicable here, because we're not really saying that exists an x at all. we're saying that there is at most one x, it doesn't mean that there is one at all. That part is taken care of by this first part. This is the one that says there exists at least one. But for the second part of the statement, the second part alone, this part alone, does not guarantee that there is at least one x at all. So clearly we have to quantify variables here, because we're talking about the quantity of x's, right? We're saying there can be at most one. So it's about quantity of the x's for which alpha x is true. And so if we can't use the existential quantifier, then we have to think of how to use the universal quantifier. But now the universal quantifier will be talking about arbitrary things, right? And then kind of continuing to think in this way, eventually you come to the following idea. And so this is the right time to pause the video if you haven't done so yet. Think about it on your own for a little bit before you hear what I have to say here. So the idea is to do it in the following way. To say that something is at most one of a certain characteristic, we can say that if we have two objects, so any two objects, and this is where the universal quantifier comes in, any two objects, and that's actually an abbreviation for this. So for every x and every y. Now, you see at this point, when we have for every x, for every y, x and y represent arbitrary objects, right? They could be equal to each other or not. We're going to think of there being at most one x in the terms of if there are two of them, they must be the same. So if there is an x and there is a y, so whatever x and y we are given, you see it's the same thing as to say if there is an x, if there is a y, and you say something after that about x and y, the same as to start off by saying for every y, for every x, or the other way around. So for every x and for every y, if alpha x and alpha y are both true, then they must be equal. This ensures that there can't be more than one x such that alpha x is true, because as soon as there are two of them, as soon as there is a second candidate here, if that y also has the same property, then y will have to be equal to x. And so that's the same as saying that there is at most one x such that alpha x is true. Okay, so we had an example here of how to express that there exists unique x such that alpha x is true. We presented two ways of expressing that. The first one had just one quantifier at front, and then so a long formula inside it. In the second one, we split up the sentence into two parts, where each part has its own independent meaning, namely the part that says that there is at least one x, and the part that says there is at most one x. And very often it's useful to say there is at most one x for something separately. So the second technique is more useful because it's more applicable. You can now take this fragment here and use it whenever you need to say that there is at most one of something, without necessarily knowing that there is also at the same time at least one, hence making it unique. Of course, these two different ways of expressing that exists unique x such that alpha x is true, these two different ways are supposed to be equivalent to each other. They're supposed to be equivalent to each other through mathematical proof. So it should be possible to prove that if one holds, then the other will hold, and vice versa. So in other words, it should be possible to prove the following. And we're going to have something now quite long. We're going to formulate this as a theorem. So this theorem will tell us that this way of stating what we wanted to state and the other way of stating the same thing are actually equivalent to each other. And so how to formalize a theorem like that? Well, we can just take this part here, sorry, I just need to copy this here. I copy this, and then I'm going to paste it here. I'm going to make it a bit smaller. And then I'm going to put this in brackets. And I'm going to put this equivalence symbol. And I'm going to put the other one in brackets here. So we copy this. We paste it here, and then we also have the other part. There we go. You see, we get a very long theorem. Which would now require proof in order for us to be certain that these two different ways of representing that the statement there is a unique x are actually equivalent to each other. Remember, this is the symbol for equivalence, so that's why we put it like that. This theorem is actually a good practice example for explaining how to prove theorems written out as mathematical symbolic expressions. However, we haven't yet touched on the techniques for laying out the proofs themselves. So we're not going to prove this theorem, but we might return to proving this theorem in a different video when we will be ready for it. Okay, so we had one example of expressing a statement of the kind that occurs quite often when we want to translate English mathematical statements into purely symbolic mathematical statements. And now let's look at another example. Very often we want to say that there are at least two different objects having a certain property. So the existential quantifier only tells us that there is at least one object x having that property. But what if I want to say that there is at least two? Would it be enough to say that exists x such that alpha x and that exists y such that alpha y? So would this be good to say that there are at least two? Because you see, one is x and the other one is y. So that's how we get there are at least two. But actually, this is very much wrong. And the reason why this is wrong is because, as we said earlier, the meaning of the x value is not retained as soon as we leave the brackets. And so once we leave this sentence, this statement, so the scope of the existential quantifier is here. It applies only to alpha x. And once we leave that scope, we only know that alpha is fulfilled for some value, and we have no access to that value anymore. And the same goes here. And so the two parts are actually then saying the same thing. They both say that alpha is true for at least one value. We cannot really compare the x and the y there, because outside the scope of the quantifiers, they're gone. They're not usable anymore. It's a bit like if you've done some programming, computer programming, right? You know that when you introduce a variable within a function, then the variable usually it's not accessible outside the function, right? And so similar phenomenon is taking place here, of course. Keep in mind that computer programming was developed after logic was developed, so it is not surprising that there are so many. I mean, we just mentioned one now, but there are actually quite a lot of similarities between the two. And I would imagine that to a large extent, computer programming was developed by applying the ideas one gets from mathematical proofs. Okay, so if variables x and y are not accessible outside their scopes, maybe we can then do it this way. We can say there exists x and there exists y such that alpha x is true and alpha y is true, where now, by placing the invisible brackets, we can be sure that within the scope, within this place where we are saying that alpha is true both for x and y, both x and y have a meaning. And this is true because there exists quantifier, has a scope which is this thing here, and there exists quantifier has a scope which is that, and so both of them are defined within that area. So now we're saying that exists x, that exists y, such that alpha x is true and alpha y is true. Does this say that there is at least two different x and y, such that alpha is true for both of them? Unfortunately, still, it doesn't say that. Now, it doesn't say that for a different reason than before. Well, in some sense, related one, but still a different one. So, for example, in arithmetic, if you write x plus y equals 4, and you ask yourself, what are the possible values of x and y such that x plus y is 4? One of the possible values is x equals 2 and y equals 2 as well. So this shows that in a mathematical discussion, if I use two different names, if I use two different variables, those two different variables could represent the same object. Like here, both x and y represent the object number 2. So the fact that you've called them by different names does not mean that they're different. So here, x and y could be the same object. And then, because of that, this is saying nothing more that there exists at least one object for which alpha is true. And so if I want the y that also must exist here to be different from x, I need to indicate that explicitly. And I can do that by inserting another ingredient here, which simply tells me that x and y are different from each other. So not true that x equals y. And so this should be also placed in brackets, but now there are too many brackets. One can drop some brackets here because it's obvious where they should go. So a version with less brackets would be the following. With less brackets plus abbreviation. So x not equal y is an abbreviation for not true that x equals y. There we go. We can't we can't remove these brackets, these ones, we can't remove them, because if we do, it becomes no longer so obvious that these are not grouped like that. This could have been grouped like that, and then the x here would have nothing to do with that x anymore because the scope of the x is gone, but still this could be a different x. And so we can't remove those brackets. And so these brackets, they must stay there. So now we've looked at an example of how we can write in a symbolic mathematical statement the fact that there are at least two different x's such that alpha x is true. Or there are at least two different objects having the property alpha, when it is clear what the property alpha is for a given object. Okay, so a good exercise for you to try on by yourself now would be to see how you can express that there are exactly two different x and y such that alpha is true for them. So this gives us that there is at least two different, and we looked previously how to say that something is at most one, and now it will be interesting to see how you could phrase something being at most two. And so that's a little exercise for you. And you can pause the video again, try to solve that exercise, and then come back to the video, because now we're going to explain how to do that. So what if now we want to say not at least two, but at most two? So instead of saying here there are at least two different x's, we now want to say there are at most two. How do we do that? There are at most two values for x such that alpha x is true. How do we say that in the symbolic mathematical language? Well, just as before, we can't really use the existential quantifier here, because we're not claiming there is even at least one. We're just saying that there can't be more than two. So like before, I guess we'll have to follow the same strategy of using the universal quantifier. And if we are very careful at observing what we did the previous time, basically we said there that if there are two, they must be equal, because there must be at most one. So saying that there are at most two, we could say that by saying that if there are three, then out of these three, two should be equal to each other, so that the number is reduced to two, right? So let's see how we can do that. So for every x, for every y, for every z, such that alpha is true for all of them. Now I want to say that two out of these three are equal. So just like I did before I wanted to say that they're both equal to each other, right here. And now I want to say that two of the three are equal to each other. How to do that? The thing is that we don't know which two are equal, right? Because once we pick specific x, y, z, it could be that x and y are equal, or it could be that x and z are equal, or it could be that y and z are equal, right? So there are basically three possibilities. And we could maybe use the symbol for or to say exactly that one, the second or the other possibility should be true. So x equals y, or y equals z, or x equals z. That will ensure, so every time you've got three variables, if you figure out that two of them are equal to each other, that ensures that you can never have more than two values for x such that alpha x is true, right? And it's not just ensures, but is actually equivalent to that. There is also another way to do the same thing, to achieve the same goal. We first begin with two of them that we know definitely are different from each other. Right? And then we say, actually I will not need these brackets. So we will begin with two that are, for which alpha is true, but moreover we know for sure they're different from each other. And then we can add to this that now if we have a z such that alpha z is also true, and then again we don't need those brackets there. Then it should follow that z must be either x or y. So we still need to use or here, but just once. I mean, overall, this does look a bit more complicated than the previous one, but just to show you that there could be multiple ways like we saw before. Let's just talk here about the importance of this part. So could we drop that part? Well, the thing is that if we drop this part, these x and y already might be equal to each other, and then it's possible there is a z which is equal to neither of them. But if x and y are already different from each other, then a third one must be one of the two. And that's what the second version expresses. And once again, as before, these two versions are equivalent to each other, and that can be stated as a theorem. So what is a theorem in mathematics? A theorem is a mathematical statement. It must be a very precise statement, as precise as it is needed in order to know how to express it purely symbolically. If there is a doubt what the purely symbolic expression for it is, then we don't regard such a statement as a precise statement. So there cannot be a doubt there, otherwise it's not precise. And in fact, the symbolic statements are there in order for us to enforce and ensure precision. And they're very helpful because as soon as you formulate something with in the symbolic form, then you know for sure that you've got a precise mathematical statement. You still might not know whether that statement expresses what you wanted to say or not, but that can be tested by applying it to the different examples and seeing whether the statement gives you the same result as what your intuitive idea gives you on those examples. Of course, one can never exhaust examples, so it's very much the human side of mathematics when you translate an intuitive idea into a mathematical statement. It doesn't take away anything from pure mathematics, though, because pure mathematics does not claim that it should be applicable. So even if you translate your real-life problem into a mathematical model, as long as your mathematical statements are precise and they will be if they're in a symbolic form, then all the mathematical side of the things will be good, even if you later discover that your mathematical model doesn't actually express what you want it to express in real life. But that's not a mathematical problem. That problem is outside the scope of mathematics, because the purpose of mathematics, the internal purpose of mathematics, is for it to be precise. And when you apply mathematics, that's when you care that your precise mathematical formulas do match the real life, and they will never perfectly match. There's always some approximation to that also. And so that's why you need to run experiments and test various different real-life scenarios to see if the match takes place or not. And that's also why mathematical models would be refined after such experiments to give a more accurate description of the real-life phenomena and so on. But all of these issues are issues for the applied subjects like applied mathematics or physics or chemistry, and all these subjects which take the mathematical models and then interpret them and apply them in situations which are not mathematical, like the real-life observable phenomena. Okay, so we've got a theorem here, another long, complicated theorem, which we're not going to prove. And I think I was talking about what a mathematical theorem is. So a mathematical theorem is a statement that can be formalized very precisely in the symbolic form, and for which there is a proof. So there must be a valid proof, for example, of the kind that we will learn how to set up these proofs in bracket notation. So every mathematical theorem has a proof in that notation that we're going to learn in this series of videos. And if you can carry out such a proof, then you can call your mathematical statement a theorem. And just to remind you what we discussed in the general overview of the bracket notation, the way the proof of a theorem like this will look like is you will begin with an empty line, so that you will just ignore that part because there's nothing that goes there. And then eventually you want to make conclusions, and some of them will be assumptions, and then you'll be stepping out of the assumptions like we discussed, and so on. And eventually in your last line you want to arrive to the statement of the theorem. So you want your last line to be this. And if you can achieve that, now this is no longer visible, but it's fine because it's the same as the statement of the theorem. So if you can achieve this in such a way that this proof is structured by the rules we're going to discuss in these videos, then you've got a valid mathematical proof of your theorem. And if a theorem does not have such a proof, then it's not called a theorem. Okay? So intuitively, of course, what we're doing here is that we are basically showing that we can come to this as an eventual logical conclusion by a series of steps of applying basic rules of logic that take us there. And so if each logical step follows the basic rules of logic, then we can be sure it's a correct logical step. And then if I have a sequence of 25 correct logical steps, then I can be sure that where I arrive to with these 25 steps, namely the theorem, is correct as well. So that's how a mathematical proof works. Okay, great. So the purpose of this video was to look at some examples of how to translate an English statement into a mathematical statement. And we looked at a few examples which are highly relevant examples. Very often we encounter this need for expressing statements such as these, the existence of a unique x having a certain property, or existence of at most one x having a property, or at least two different x's having a property, or at most two different x's having the property, and so on. So these kinds of statements are very common in mathematics, so it's very useful to have gone through these examples. However, I hope that this video has a reach beyond these examples. I hope that by going through these examples step by step, you also can figure out a kind of general skill that you can acquire from this exercise of how to do such things for other statements which are completely unrelated to this one. I hope that these examples kind of gave you a flavor of how to do such things. Eventually, there is a point after which you will see that you can express any kind of statement using symbols. So a professional mathematician will never find a statement that is impossible to write out symbolically like this. And so this is good news. It's a skill which you can refine to the point that it becomes perfect. So it's something that's definitely doable. It's not something mysterious where it's not clear. Like some of the mathematical problems, it's not clear whether it's possible to solve the problem or not. In this case, it is quite clear. It's always possible to solve. Of course, when the English statement is ambiguous, then there could be multiple different versions which are not equivalent to each other. But when intuitively something is precise, it is always possible to find a symbolic statement that expresses it, no matter how complex ideas your intuitively precise statement describes. Great. So that's the end for this video.